Okay, good morning, Astronomy 1020. Welcome to our 12th lecture. Today, we are going to discuss general relativity, which is going to be useful for us to learn about the death of stars. Everyone looks particularly engaged doing other things. Let's start by hiding the video trolls, because we don't need no trolls. And let's talk to a few of you who are doing what you're doing. So what if we had to discuss the differences between special relativity and general relativity? That's the business of today. I'd like to say that today I kind of designed it as a pressure relief valve because you guys are, particularly busy during this holiday season. I thought that, we wouldn't have a lab this week since we only have one lecture. There's no homework. We'll just kind of catch up with the relativity stuff we learned about, talk about one of my favorite subjects, general relativity, and then we'll be well prepared to discuss the death of stars next week, which is chapter 18. So, a short, quick, and hopefully somewhat fun lecture today. But first, I need some of you or one of you to sort of interact with me and tell me if you know what the difference is between special relativity versus general relativity. Both of these theories were proposed by Albert Einstein. They were proposed 10 years apart. First came special relativity in 1905, and then Einstein set out to work on his more general theory and completed the work in 1915, 10 years later. Now, you don't know too much about this subject yet, but I'm hoping you know a couple of things about special relativity. The question that I had, the test that I have for you, Runsack, is can you tell me what is so special about special relativity?
I'm going to read out of my notes. Laws of physics stay the same in all inertial reference frames, and the speed of light is a constant.
Okay, what you just read to me, Runsack, are the defining postulates of special relativity. And you bet I'm going to test you on those. So make sure you got them memorized, or here's the secret. Make sure you've got your notebook handy when you take the test, right? I guess you don't have to memorize things if your notebook is right there. But you do have to know about the concepts so you know where to look. You just told me about the two postulates of special relativity, which is where all of the wacky weirdness that we discussed last week come from. But that still doesn't answer my question, Runsack. And I'm not even sure if you can answer it. I'm seeing what you know, right? Why is it special relativity? Why isn't there just one relativity? There's two different branches of relativity. Usually you learn this one first. You actually follow in the footsteps of Einstein. Einstein discovered this one first. He came up with his postulates and followed through with their conclusions. You have things like time dilation and length contraction and mass increase. And then why would he set out to discover general relativity? Yeah, give it a whack.
My guess is that special relativity is it specific to a frame of reference, and then general is the more like third-person view of each frame.
You don't think he's rental?
That was a noble effort, Runsack, but unfortunately not correct. In fact, it's even simpler than that, okay? Well, it does have to, hold on, Runsack, let's talk about where you were reaching towards goodness. It does have to do with reference frames. It is about inertial. Hey, by the way, what's an inertial reference frame? Do you know what an inertial reference frame is, or could you look it up in your notebook? What is, you said the laws of physics stay the same in all inertial reference frames. That's great, but what the hell is an IRF anyways? Special relativity deals with inertial reference frames. And basically, relativity only holds sorry, let me try that again. Special relativity only holds in inertial reference frames. Arunsak, did you find that in your notes?
Remember how I wasn't there for the class? I don't have that note.
Oh.
Yeah.
Well, this is a great job for the other student who's participating with me today, the only other human being who I get to interact with, Christopher Leonard. Do you have notes on that subject? Who's in the troll hole today? Oh, actually, Devin Irons. I missed him because he was in the troll hole, but he's chatted to us a perspective when a velocity is constant. Now, Devin, I don't know if you were answering this question or this question, but either way, your answer is correct. And well, I don't like the word perspective. Perspective makes it sounds like it's an opinion or like, I think astrology is relatively interesting. That's my perspective. Hello, Caitlin. Thank you for joining us and being a third. Yeah, turn your camera on, Scrubs. I love it. Thank you for being a third human being that I get to interact with today. Okay.
You're welcome. Sorry.
You're looking very fuzzy. Okay. You're not trying to get bullied all class. Okay. You're not getting bullied. You're getting the love and attention that you paid for. Okay. And don't forget, students. Actually, can we just have a second here? A digression about homeworks. I did do my job on Sunday. It was, I barely did it, but I did it. And I graded all your papers. And one thing I discovered is that not everyone is turning in their stuff, which is something I already knew was going to happen. But sometimes it's those of you who I think are actually in class. And I'm thinking about Austin, who's not here today. Austin certainly missed one of his homeworks. Now, if you share your video with me and you're a human, then I know who you are, Caitlin, Arunsak, and Christopher, okay? So I'm keeping an eye out for you guys. And if I see you guys miss stuff, I'm going to personally get in touch with you. The trolls are a different story because I tend to forget the trolls. Devin talks to me a little more than the average troll, so I'll keep an eye out for Devin too. But for the most part, if you're in the shadows, I strongly suggest that you go into your grade history in Blackboard and make sure that all the homeworks that you think you turned in are actually turned in. Because some of you, I think, start loading it and then exit Blackboard, and it leaves it as a in progress file, which I do not get in my grading center. So do you understand what I'm saying? This is an important thing. Like Caitlin, Christopher, Runsack, you guys are here with me every day. I would expect you guys to have everything turned in, but every now and then something will slip through the cracks. And the problem on my end is it's difficult to keep track of you and my other class because there are so many names in the list. Like I said, you guys I remember, so I'm trying to keep an eye out for the humans. But for the subhumans here, you should definitely go and take a look and make sure that all the grades that you think you turned in are turned in. Because there's a lot of you for me to keep track. Anyways, okay, so that's it. That's all I'm gonna. Where is the grade thing, Gianna? I don't know how it looks in your Blackboard. I can only tell you how it looks in my Blackboard. And so maybe I can give you guys an example here so that you understand what I'm talking about. Can I still turn homework 7? Well, Caroline, we're going to have a conversation about that offline. Maybe I'll allow it if you're very nice about it. You'll have to, explain to me what happened there. But in general, once I grade the homeworks, I want to shut them down so I don't have to keep, there was one year where I had absolutely no rules, which is my natural tendency. And then there were students who did nothing all semester. And then the last day of class tried handing me every single homework in lab in one shot. And I was so fucking angry with them. And that was bad for me. Like I was under the most stressful time of the year. I can't have that, right? So Caroline, we can talk about it, but you're going to have to be a human being and interact with me at some point. It doesn't have to be during class. Send me an email and then give me your song and dance and we can talk about it. Especially if what I wanted to share with you guys, because Gianna says, where's the grade thing? Hold on. Are you guys, am I? let me share my screen again. Sorry, I'm a little distracted today. When I go to my grade center, I don't know how it looks on the student side, but I have a little bubble here that says needs grading. You can see I've graded everything, so I have 0 items to grade. But sometimes in the grade center, I'll see students who think they've turned in an assignment. Like,
Professor,
yeah.
can you check if I'm missing anything since you're already there right now?
Or more.
Yeah, see where it says attempt in progress? I can't always look at that. So Reese Bullock thinks he's turned in homework 1, but he didn't. So that's the kind of thing that I'm worried about. So first of all, Arunsak, everyone should be, yes, I'm going to do it for you because you interact with me every week. But wait, Arunsak, what's your last name again?
CHHUN.
Right. Okay. Yes, you have everything. You have everything. But for the most part, you guys should go into your own. Okay, Jesse Ward, no, this is going to turn into chaos. Here's an idea, Jesse. You go into your Blackboard and scroll along and see if you have everything. Okay, that's an idea because I can't do this for 40 people. I get to do it for Runsack because he shares his lovely face with me. You do not. That's the penalty for being a troll. Okay, Jesse, much love, but all you got to do is just go and scroll through your own thing. Don't make me do it. All right. Let's get back to the game here because we're supposed to be talking about science and that's the goal. Okay. All right, Kevin. Well, you got to send me an email and we'll talk about it, okay? What makes special relativity special is that it's a restrictive, smaller domain of general relativity. And it deals only with motion at, actually, hey, Caitlin, now that I've got a third person to torture, what's an inertial reference frame? Do you have that in your notes? I bet you do because you're such a good student. Look it up while I get some iced tea. All right. Sorry, but this class is going to require a lot of iced tea. Caitlin, did you figure out what an inertial reference frame was?
A coordinate system that moves at a constant velocity.
Oh yeah, that's what I want to hear. That is what makes special relativity special. It only deals with motion at a constant velocity. Underline that. This is the idea behind special relativity. Can you guys give me an example of a constant velocity? What would be something that moves at a constant velocity?
The speed of light.
Good one. Very, very good one. In fact, Arunsak, I'd go as far as saying that's the only thing in nature that actually travels at a constant velocity. Because let's try to think about other things that move, right? Does a dragonfly move at a constant velocity? No. Does your car move at a constant velocity? Well, entanglement's a different thing. If you take a trip to the store in your car, you start off presumably at rest with respect to the ground, and then you accelerate to get moving down the highway. And as you travel down the highway, you're never traveling at a truly constant velocity, but you're making you're traveling at microscopic velocity adjustments when you take a corner. Hey,
Wait, what about gravity?
Constant velocity if you sit on your couch and play video games? Arunsak says yes. Then is that an inertial reference frame? What do you think, Christopher? Is sitting on your couch playing video games an inertial reference frame?
I would say no.
Why not?
Okay, like, yeah, when you are doing that, you're at a like sort of constant velocity. but it doesn't stay that way. You're
Well,
still gonna get up and move.
not to be okay, but not to be pedantic, Kevin Ryan was trying to remind us that 0 meters per second is still a constant velocity. But my point is something different. Here you are, you're sitting on your couch on planet Earth, right? And here you are in Rhode Island, presumably, and you're, let's make sure the Earth goes the right direction. You're spinning like this. If you're on a rotating Earth, is that a constant velocity? Does Earth rotate at a constant velocity? I mean velocity, Arunsak, not speed. What's the difference between speed and velocity?
Velocity has direction.
Okay, so here you are in a spinning Earth. Is that a constant velocity? If you are a point particle spinning on this globe, is your velocity constant?
I would say yes.
And you would be wrong. Okay. So the idea is, Arunsak, motion in a circle is not constant velocity. Does that, let's try to look at it, okay? So forget about the Earth, although if you are at some latitude on Earth, you're spinning around in a circle, right? And one moment, so this is you, okay? One moment, your direction through space points like this. And then as Earth rotates, now you're over here and your direction points like so. And now you're over here and your direction points like so. And now you're over here and this is not, motion in a circle is not a constant velocity because you have centripetal acceleration, right? You're going around in a circle and there's something that is forcing you to keep changing your direction through space. You ever go to one of those amusement parks and go on the tilt-a-whirl or the teacups? The thing that it's like the thing that makes you want to vomit, you spin around and then the whole thing spins around. How does that feel? You feel forces, you feel centrifugal forces acting on you as your body is crushed into the side of the teacup. Do you know what I'm talking about? Yeah. When you start, or let's take an even simpler example. If you take an exit ramp, you can feel the car pressing against you as you move around the corner. You can feel as soon as you start moving in a circle. My only point is this: even if you think that you're in an inertial frame, you're not, because you're on a rotating Earth, which travels in a circle. The planet itself is in a circle around the sun. The sun itself goes in a circle around the galaxy. And guess what? The galaxies are moving towards each other as well, or sometimes away from each other. It depends which one you're on. So Einstein worried about this. He worried that this was a weak-ass version of general relativity, which could only account for motion at a constant velocity. And pretty much there's only one thing in the universe that travels at a constant velocity. And was it Christopher or Runsack? Who said the speed of light? That was brilliant. That was exactly the best example.
It's Christopher.
From 2 to 3
Right, Christopher.
hours.
That was the best example you could have given at a motion at a constant velocity. Anything else you said basically would have been wrong. Okay. But here's the deal. If we begin to accelerate and we go from 0 to some velocity, do you think that the effects of time dilation and length contraction will suddenly stop and switch off? Does it make sense to you that time dilation only happens if you're traveling at a perfectly uniform speed, and that if you speed up or slow down, none of those effects should be there? Do you understand what I mean? Does that make any sense? Okay, well, first you have to believe that time dilation exists. I went through great pains to tell you that it does. Yeah, Cameron's saying if you start to go faster and faster, in general, we discovered, right? We discovered that you get more time dilation effects the greater your percentage of the speed of light. So if we look at time dilation, the observer time is gamma times the rest time. And you guys remember gamma, right? The boost? That's your special relativity whack factor. And your gamma is 1 over the square root of 1 minus v over c squared. Since we usually just put in our percentage of the speed of light there, sometimes people make a substitution where instead of writing v over c, they just write beta, which is your percentage of the speed of light. Beta is your velocity expressed as the speed of light. For instance, a beta of 0.9 means you're traveling at 90% the speed of light. As your percentage of the speed of light increases, your gamma gets bigger and bigger, and your time dilation grows. Your length contraction contracts. And who was the troll who said that? Or yeah, Cameron said, look, if you speed up, I expect there to be more time dilation. And so did Albert Einstein. But here's the problem. His theory of special relativity could not account for those effects. So Einstein went on a 10-year quest to master how accelerations would affect time dilation and length contraction. And what he did not expect, perhaps, but what happened is he discovered a new theory of gravity by doing so. So let's see if we can't get into that a little bit, all right? So that was a big buildup for general relativity in hopes that you would remember the difference between these two things. General relativity, published in 1915, now 105 years old, if you think about it, was an attempt to deal with the question of how does acceleration affect? I don't even want to finish that because it turns out to have a variety of different effects. How does it affect relativity, should I say? Or how does it affect these things that we've discovered from special relativity? There is one version of the two postulates of special relativity for GR, and it is known as the principle of equivalence. Sure hope I spelled that right. The principle of equivalence was Einstein's key insight that helped him master this theory. And it has two different versions. Actually, it's got a couple of different versions, but we're going to give you a simplified one. It has two different aspects to it. One basic idea behind the principle of equivalence is that the effects of gravity are equal and identical to a pure acceleration. You can call this version 1. There's another version of it, version 2, which is a free falling reference frame. So this is a key term here. I'm going to explain all of this. A freely falling reference frame, where presumably you're falling in a gravitational field, is identical to pure weightlessness. Now, to help you understand this, I've got a couple of different pictures, but let's start off by going to the movies. There's a movie that I like very much, an old, I think it's an 80s movie, called Dark City. I don't know if you guys have seen this, but it's a pretty goth kind of film where there are all these characters meandering around a complete nighttime landscape in a city, and their memories keep failing and they can't figure out what's happened to them. And slowly the characters begin to, wait, does anyone know about this in the chat log? That movie's
do.
depressing. I thought that movie was so cool. I rewatched it recently. The reason why I'm thinking about Dark City right now, let's see if we can get like a visual from it. It's kind of dark, and the characters are meandering around this nighttime city, which keeps shifting on them, and they slowly begin to realize, to their horror, that they are not really on Earth, but they are on this massive alien spaceship designed to look like Earth, that's traveling through the galaxy in some kind of crazy psychological experiment. Awesome film. Gotta watch it. Okay. What if we were in Dark City? You know, what if we were in a classroom that was propelled through outer space with a constant acceleration? You could actually mimic the effects of gravity without there being any gravitational field. For example, and here I'm going to use one of my crappy slides, somewhat less exciting than Dark City. All right. What if we were in spaceship classroom? Okay. When you're normally in a classroom, let's see if I can draw here. You're a dude or a dudette, and you are standing on the ground, or you're sitting in your chair, and you may not be conscious of it, but you are feeling a acceleration that pins you to planet Earth of 1g, 10 meters per second squared. This is why your feet stick to the floor and you don't float away up to the heavens, okay? Suppose, just like those boxcar trains from special relativity, that we designed a spaceship classroom. It had 4 walls and a ceiling, and there were no windows, so you couldn't see outside, but we attached some kind of rocket thrusters, and we're not going to just let it travel at a constant velocity. We are going to undergo an acceleration. We will fire some thrusters, some very quiet thrusters, at the bottom of the classroom, and we will propel ourselves forward at an acceleration of 10 meters per second squared. The effects that you would feel from that accelerated classroom would be the floor smashing into your feet and pushing you forward through space. But your psychological experience of it would be identical to gravity. You would not feel like you were being pushed forward in spaceship classroom because you're used to a classroom being at rest and being on the ground or something like that. All you would know is that your feet were somehow pinned to the floor, and you would experience it as a form of gravity. Einstein took a conceptual leap from this point, and he said that whether you are in a true gravitational field on Earth or whether you are in a classroom that's accelerating at 1g, it doesn't matter. They are the same thing, which is totally preposterous because they're clearly not the same thing, right? It's not the same thing to be stuck on planet Earth versus being in a spaceship. You would think they are different situations, mostly because this involves a gravitational field, and oops, this one does not. The story of how this is the secret to how Einstein developed his theory of general relativity. And when I read the history about it, Einstein said in one of his letters or one of his papers that the whole way that he developed this insight was there was a bricklayer or some kind of construction worker who had been working in the German city where he lived a few blocks away, and he fell from like a 6-story ceiling or a building, and he fell down to earth, a fall that should have just killed him. And for some reason, he landed in such a way where he survived, and it became like a local sensation, and all the local newspapers interviewed him, the bricklayer who falls from the roof and doesn't die. And they asked him, what was your experience like? And he said, you know, as I was falling, I really didn't feel like I had any weight at all. I felt like I was floating free in outer space. And from that one newspaper article, that's where Albert Einstein developed his idea of the principle of equivalence, which helped him come to general relativity. Let's talk for a second about what we call a free fall reference frame. Suppose you're inside of an elevator. And elevators make an ideal situation because it's a box with no windows. You know that you're moving because you can kind of feel the acceleration of being pulled up or down, but you can't see the world outside you going by. Suppose someone took the scissors of God and they snipped your elevator cord while you were inside a very tall building, and you were to suddenly go through a free fall plummet to your doom at the bottom of some building, just like this bricklayer. As you know, Galileo taught us an important lesson about gravitational fields. Whether you're a ping pong ball or whether you're a stone, all objects fall to the ground with the same exact acceleration, independent of their weight. Do you guys remember Galileo and the inclined planes? The whole purpose of that experiment was he determined it didn't matter if your sphere was made of lead or if it was made of wood or rubber, all objects fall to the earth with the same acceleration, independent of their mass. If that's true, and we know it's true because we've done the experiment millions of times, a person will fall to the earth at the exact same acceleration as an elevator. You and the elevator fall to the ground with the same acceleration, and during the descent, you will move and be free, independent of the elevator. You would suddenly find your feet no longer pinned to the floor, and you would float around as if you were weightless in outer space. Einstein reasoned that if you actually took a person inside of an elevator, a sealed tight elevator, and you brought them deep into the vacuum of space, far removed from any gravitational field, no stars or no planets around, that person would also float weightless. And if you were the dude or dudette inside the elevator, there would be no physical experiment that you could conduct which could distinguish the two situations. In effect, once you are inside one of these free-falling frames, you cannot distinguish yourself from a lack of gravity. Of course, you'll distinguish yourself once you hit the ground. That will be a different story. But up until such happens, up until that moment happens, the two reference frames are non-inertial. They are, well, actually, here's the real messed up thing about it. One of these frames is an inertial reference frame. Which one? The left or the right? One of these frames is inertial. Does anyone understand me? Oh, wow. Thanks, Christopher Leonard. The Empire State Building, huh? If there's an essay on that or something, Christopher, you should share that with me. Anyways, I have to ask you guys questions occasionally to make sure that somebody understands me, which is not always the case. One of these two, this is a reference frame that's falling to the ground on Earth. On the right-hand side, we have an elevator that's floating free in outer space. One of these reference frames is inertial. Which one is it?
The right one,
Yeah. Why is the right one technically an inertial reference frame?
because it has a constant velocity.
Which is 0, right?
Yeah.
Yes. Beautiful. That's exactly what I want to hear. This is not an inertial reference frame because it's undergoing acceleration. Okay, Caitlin, now that you have correctly answered that question, I'm going to pull the sock inside out and say Einstein, his concept was that they're both inertial, which is kind of messed up, right? He's saying that this, by the principle of equivalence, is identical to this in almost every way. Now that you've heard that story, let's draw a picture and see what he did with it next. Unfortunately, unlike special relativity, where we had a few equations that you could grapple with, general relativity is mathematically much more complex than special relativity. It takes, well, not a lifetime, but it takes a while, many years, to master the mathematics necessary to do this. And I want to encourage you guys, you know, from time to time, my students do go on and study astronomy and physics, and it can be such a short time, really, between you sitting in a classroom and you being in a undergraduate program or a graduate program somewhere. A couple of my former students who were once sitting in the same, well, maybe not the exact same chairs because you guys are at home, but one of my former students, Jason, now he studies this stuff and he's going to graduate school at the Rochester Institute of Technology. And that's, it's a beautiful thing. I'm actually a little jealous. Let's see how we can take this concept without mathematics and discover one of the things that Albert Einstein did. So what we're going to do is we're going to construct a sort of thought experiment with a planet, all right? So this is a planet like Earth. And this planet has gravity. And we're going to construct ourselves two observers who are undergoing a kind of free fall like experiment. Observer A will be standing on the ground, and they will be conscious of the gravitational effects. And observer B will be in an elevator in which the cord has been cut. And I'm going to draw the elevator at two different steps during its descent. So I'll try to make my elevator, I'll make it 15 centimeters here and here. Make it. I'm just going to make it a box. All right. So this is a free falling reference frame, and we'll put a second observer, observer B, who's kind of floating weightless in the free fall frame. And this will be two different times during the motion of descent. This will be your start time to the experiment, and this will be the end time. Let's assume they're nothing more than a few seconds apart. Hold on, guys. I'm just going to adjust the heat in here. Sorry, I was starting to overheat. By the way, before I go on with this, let me just say one more thing. You guys can conduct a version of this yourself. If you've ever gone to an amusement park, they sometimes have those rides which are called the free fall. I don't know if anyone's ever been on one of them. Maybe we could find a YouTube video. Do you guys know what I'm talking about?
Like Tower of Terror.
Yes.
Yeah.
So you've gone on one of those? Apparently, believe it or not, I have never gone on a Tower of Terror, but I really should, since they're an important part of my lecture here.
They're fun.
They're fun. Apparently, you're not supposed to do this. People freak out over it, but apparently, if you are on one of these free fall rides, you can take a quarter and you can put it on your knee during the descent, and during the duration of the fall, the quarter will kind of levitate and float weightless over your kneecap. I've heard this is like a fun thing to do. Obviously, the people at the amusement park get really upset because once the quarter hits the ground, it goes flying somewhere and it could potentially hurt someone. But if you're daring, if you're risky, you can actually put a little penny on your knee and watch it hover and float weightless. That's kind of a cool proof of concept, shall we say. Or, next time you're on one of those, I want you to think about it. What if we did an experiment during the descent that was very similar to one of the ones that we did for time dilation, where we fire a laser from one part of the car to the other part of the car? So what I'm going to do is I'm going to take a red laser. I'm going to use blue for the laser handle. Okay. So here's your little laser lever, or this is your, it's this thing, the thing that you fire the laser from. And we're going to put it a particular height above the ground or above the bottom of the elevator. And we'll just call it little h. Little h is the height that the laser is positioned above the floor of the elevator. I'll try to make it about the same for both. And what we're going to do is during the descent, we're going to fire a laser from one side of the car to the other side of the car. Nothing fancy, all right? And of course, that laser will strike the other side of the car at the same height little h, from the ground. Beams of light, laser beams, presumably travel in a straight line until they reach their destination. This is something that we can all imagine if we use a laser pointer. When you fire it at the screen, it tends to travel in a straight line until it reaches its destination. Suppose we conducted this experiment somewhere in deep space, far from the effects of any gravitational field. We know exactly how it would work. You would be in some distant part of the, I don't even want to say galaxy. I want to put you in deep extragalactic space here. And you have your laser beam positioned above the cart, or above the floor, excuse me, and you fire your laser beam, and it should travel in a straight line, and it should hit the other side of the elevator some height above the ground. This is how light travels in space, presumably in a straight line, unaffected by any forces. How would the observer on Earth, if this was some kind of a one-way mirror elevator, how would an observer on Earth who is conscious of the fall of gravity observe this experiment? At the start of the experiment, the laser would begin to fire, but both observers would need to agree that the laser was going to hit the cart at the same height above the ground. The only conclusion the person on the ground can reach is that the light doesn't travel in a straight line. The path of the photon now goes like this. And by the way, photons do this. They curve in the presence of a gravitational field. Is that okay? That's weird. Why is it weird that a photon should curve if you're aware of the presence of gravity? You understand what's going on, right? If you fire the laser at the start of the experiment, both observers need to agree that it hits the same height above the ground. The problem is, if you're inside the elevator, what seems like a straight path for the laser is not a straight path if you're standing in the presence of a gravitational field. The path of the laser will be curved. Yeah, a run sec.
Is it because, wait, what's your original question? Why is it bending according to person A?
Well, I guess my question, it wasn't very well posed, a run sec, but the question is, why is it strange that gravity should be bending the path of that photon?
It's because gravity, like, it disrupts the space-time, so that way the photon.
A run sec, I didn't ask that question correctly. That's my fault. How does gravity work? Like, we studied Newton's law of gravity, correct? And from what I remember, the equation says that the force of gravity is equal to big G times m1 times m2 divided by the distance squared, right? What does this tell you about gravity? What do you need to have present in order for gravity to exist?
A mass, a
mass?
distance, two masses.
You need to have two masses, don't you? Gravity only works, a run sack, when you have particle 1 with mass and particle 2 with mass, and the two are attracted to each other. The problem that I see with this run sack is that light does not have mass. Light is a purely electromagnetic phenomenon. It's not solid. All right, let me get rid of this here. Let's go back to our lecture on light. A long time ago, when I defined what light was, I described light as an electromagnetic field. One part electric field, one part magnetic field. And in slide 26, you can see this time-varying electric field. These green and blue arrows represent the field of positivityness or negativityness that surrounds a charge. Perhaps an even better version of this could be found in those physics Java apps. Humor me for a second so I can try to make my case here. Oh, sorry, you guys can't see what I'm doing. Share screen. Here. A runsack, this is a particle like a proton, and a proton certainly has mass, correct? But the proton is not light itself. Light is when you take the proton, this is the positive field, the electrostatic field which surrounds it. If you give the proton a wiggle, you create ripples in the electromagnetic field. Those ripples, a runsack, are massless. In a way, try to imagine these two magnets here, right? These two magnets have a magnetic field which is invisible. It is ripples in that invisible field which constitute light. And because they're bound by the equations of electromagnetism, they do not have mass. And suddenly, a runsack, what we see is a gravitational field curving the path of a photon. That is not supposed to happen. This was a total eye-opener. It was a profound realization that Einstein had, which is it doesn't actually matter that the photon doesn't have mass. It's still being affected by the gravitational field of the planet. And this is how we came to a new idea about gravity. That gravity isn't just about two masses interacting. It's about masses warping and curving the nature of space-time around it. Okay, here we have to go on a little digression about what space-time is. So in fact, let's make sure that we write down the conclusion before I move on. The conclusion is the presence of mass from observer A's point of view has curved the path of the photon. From this concept, Einstein developed a new theory of gravity, a theory of gravity that is different from Isaac Newton's idea. How gravity works in, by the way, GR is the typical abbreviation for general relativity. It's a two-step process. First, mass curves the 4D space-time in its vicinity. So the space around the mass is actually being warped and curved itself. And then step two is this curved space-time alters the path of other objects around it, even if the other object is a photon. So it's the curved space-time. Sorry about my bad handwriting here. The curved space-time alters the path of other masses or photons around it. You're going to need a couple of pictures to help you visualize this. But take a moment to get that down. Stacy, people, can you, or Caitlin, give me a thumbs up when you've got that so I can. Emily, let me know when you're finished. Okay, Cam's good. Caitlin's good. Gouda. That's alters, by the way. Sorry about my handwriting. Especially if it's in some French onion soup, right, Cam? Emily, you still writing? Okay. I'm going to erase if that's cool with you guys. I don't want this to be too wishy-washy. We're going somewhere good with this. So just stick with me for a second. Okay, every time I try to talk to one of my friends about general relativity, usually the sticking point that comes up is they say, wait a minute, did you say 4D space-time? What the hell is that? And maybe a Runsack that was your question as well. Runsack, perhaps the best way for us to go, believe it or not, the connection between the 3 dimensions of space and the 1 dimension of time come from special relativity, not from general relativity. But general relativity depends upon us having a concept of a 4-dimensional space-time manifold. Let's start where we were last class. Last class, I talked to you guys about the Pythagorean theorem. How does that one go again? Let's do the 2-dimensional version. You guys, someone out there knows the Pythagorean theorem, right? That's like some old school. What is it, Emily?
A squared plus B squared equals C squared.
Correct. And that's for a triangle, right?
Yep.
Emily, with your permission, I'm going to actually just draw a little triangle for you guys, okay? This is 30 centimeters long. It's 10 centimeters tall. And here's our hypotenuse. Our hypotenuse is about 32 centimeters long. Instead of using A, B, and C, Emily, you may remember if you were present in last week's lecture that I changed the variables to X, Y, and for my hypotenuse, I'm going to choose the letter S, which is frequently done in relativity. So the 2D version of the Pythagorean theorem would be S squared, my hypotenuse, is X squared plus Y squared. And the reason I'm writing it this way, Emily, is to remind you students that in a way, this could be 2 dimensions on a graph paper, right? From your math class, you guys frequently have to, plot and draw points on a graph paper. And usually if you have a coordinate, we could set the origin of our reference frame here. Okay, so this is the y-axis, right? And this is the x-axis below us. And this position here, this could be a point on some graph paper. And the point would have coordinates x, comma, y. And we would find the distance from the origin by using the Pythagorean theorem. This is something I bet each and every one of you had to do in some elementary math course, or maybe even in the math course that you're in right now. I don't know. Would you believe it if I told you that there was a 3-dimensional version of the Pythagorean theorem? This equation still works if you have to make a plot in 3D. And so this would be a little more complicated to do, but imagine we took our 3 rulers and we made a little vector machine here. So I have an x-axis and a y-axis, and I guess into the plane of the board would be a z-axis. In classrooms, I can usually hold this up, but it's a little awkward to do. So here's my 3 axes, x, y, and z. And I could imagine plotting a point in 3-dimensional space. There is a 3D version of the Pythagorean theorem. X squared plus y squared plus z squared equals s squared. And if you'd like, you guys can think of the 3-dimensional Pythagorean theorem. This equation basically describes how 3D space works. If you want to plot a point in a coordinate system, you can find its distance from the origin by using this equation. Once Albert Einstein told us that the speed of light was a constant, he basically made it so that velocities don't simply add anymore, but they approach a limiting and a finite speed of 300,000 kilometers per second. From the perspective of a photon, which is always in motion, and as Christopher pointed out earlier in the class, the velocity of a photon is always constant through space. From a photon's perspective, 300,000 kilometers in space is equal to 1 second in time. And in a way, all we really have to go on with relativity is this relationship right here. The only thing that Einstein was really sure about from the onset is that photons travel in such a way that in 1 second, they always traverse 300,000 kilometers of space. That means you're pegging a certain distance to a certain time. Through this, he constructed something called the Spacetime Metric. I want you guys to think of the Spacetime Metric as the equation of spacetime, and it's kind of like a 4D Pythagorean theorem. So unfortunately, I've used up too much board space here. Can I erase this? I'm not even sure if you guys are writing this down or, okay. I'm gonna erase this. Now, normally this is just maybe just a smidge over our pay grade, but I don't think so. I think if you guys can handle the Pythagorean theorem, you can handle this. And it is in the book. So introducing the 4-dimensional space-time metric. And this is where we're going to get into some kind of weird stuff. I want you to think of it as kind of like a 4D Pythagorean theorem. The equation can be written in one of two different ways. S squared equals, and I think I'm going to write it in the way where the space is positive. X squared plus y squared plus z squared. Now, time doesn't have the same units as space. So what I'm going to do, and here's the real trick, we're going to subtract the time component. C times the time squared. This is a distance, a 3-dimensional distance through space, and this is a distance that a photon will travel in a given amount of time. And this is your path through 4-dimensional spacetime. It's known as the metric. It's an equation of how space and time are related to each other. Now, to give you guys a couple of ideas, unfortunately, it can be quite difficult to think in 4 dimensions, but we could restrict ourselves by considering a nice, simple example. I want to show you guys a slide. And it's a slide of Earth's, excuse me, let me get things under control here. It's a slide of Earth in an orbit around the sun. Just bear with me here while I find the right picture. Okay. Slide 67. What's cool about Earth's orbit around the sun is although Earth has a height and a width and a length, Earth is a 3-dimensional object, we could choose to ignore the height of Earth and just kind of imagine it as a flat circle in orbit around a circle that is the sun. What if instead of plotting distance on the y-axis, what if instead we plotted time? If you watch the orbit of Earth in a spatial dimension, you basically just see Earth going around the sun over and over and over again, traveling the same circle. Hey, bonus points if you remember the vocabulary term for this. What do we call the circular path of Earth's orbit around the sun?
Ecliptic.
Nice, Arunsak.
Let's go.
Arunsak, what would the ecliptic look like if we could plot its journey through space-time? Instead of seeing it going around in a circle, you would actually see the orbit of Earth as a ribbon winding its way through space. As the Earth constantly orbits the sun, it's always being propelled forward in time. The path of Earth, the real ecliptic in 4D, would no longer be a circle. It would be this ribbon that kept winding its way through space. This ribbon here is the space-time metric. This is S. It's the distance that you travel not only through space, but also through time. And what's super messed up about the space-time metric, the thing that you have to really wrap your mind around, is this minus sign. You're taking the components of space and subtracting it from time. All of us have a journey through space-time. And one way that you can plot or understand your journey is by making a special type of graph that we need for relativity called a space-time diagram. So just bear with me here for a second. In a space-time diagram, a person plots their position in space on an x-axis, and we're going to ignore y and z because we don't have enough dimensions to write them down in. And you plot your position in time on a y-axis. So the y-axis is no longer, it's no longer a spatial dimension, it's time. Let's imagine that you are sitting on your couch playing video games, or maybe sitting on your couch listening to a boring lecture. What would your journey through space-time look like? Well, if this is the origin, this could be, say, my apartment, and let's say you guys live several kilometers away. Here you are sitting in your chair and sitting on your couch. You are maintaining a fixed distance from me, always a good idea, and you're journeying forward in time, whether you like it or not. Your trajectory through space-time would look a little something, let's use blue for you. It would look a little bit like this. Your journey through space-time, if you sit in a chair, is a vertical line that propels you forward in time. Let's face it, this lecture is taking a long hour and a half. It's almost over, so don't worry. And during the course of this lecture, you've been sitting in your chair and you've been traveling forward in time, whether you like it or not. What if instead you started to move around? What if you took the lecture on your iPhone and you hopped in your car and you took a little trip during this class? You do not enjoy forward. I do not enjoy journeying forward in time either, Christopher. See, we have to first master the space-time metric, and then we can go back in time, okay? If you were traveling through space, let's say you got out of your chair and you started to take a run, your journey through space-time would look a little bit more like this. You'd be traveling forward, you'd be running down the street, and whatever your velocity was would be propelling you forward in time. Now, can you run as fast as a photon? No, you cannot. Yeah, Runsack says yes. A Runsack, I suppose the journey of a photon, so let's say you sat in your chair, and now we're going to fire a laser, okay? Sorry, that was my diffraction grating. We're just going to fire a laser beam forward from this little, this laser pointer here. The path that the photon takes is always going to be a bit faster than you, and according to Einstein, nothing can go faster than the speed of light. So this is the path of a photon. The path of a photon forward, in fact, here I'm going to have to clean up my diagram a little bit. So in order for me to do this right, let's get rid of you, let's get rid of the couch, and let's simply draw the path of the photon on my space-time diagram. Just bear with me here. The path of the photon, which is the fastest that anything can travel, sets up something called a light cone. And if we were to draw it in 3 dimensions, your light cone would look something like this. If you, the observer, are sitting at the origin, you can only be aware of future events that happen in time at positions that are less than the speed of light. Let me try to say this again, because this is going to start to sound like metaphysics, okay? In space-time diagrams, we frequently draw something called a light cone. And basically, I'm just telling you this stuff to freak you out for no other reason. Well, actually, also to teach you about GR. F572. Here you are at the origin. Each of these points, D, C, A, and B are called space-time events. A space-time event could be a supernova. It could be a firecracker that goes off. It could be you swatting a fly. All of those things happen at a particular point in space at a particular point in time. Here's the messed up thing about the speed of light. The speed of light limits what information we have access to because information travels at the speed of light. If I call you up on the phone, our voices can only connect to each other at the speed that light takes to travel. They're basically radio signals. It's radio photons coming out of our phones. Things that happen inside your light cone at velocities less than the speed of light, these are called your future. And things that happened back in time within your light cone are called the past. Then there's this creepy part of space-time they call the elsewhere. The elsewhere are regions of space-time you do not have access to because light or information cannot travel to you faster than the speed of light. And I could give you, I know it sounds kooky, Caitlin, but let me give you a very simple example. The star Betelgeuse, which we've talked about before, is 600 light years away. And I think we all had a conversation about one day it could go supernova, and that would be a pretty wild thing to look at, right? If Betelgeuse went supernova today, right now, how long would it take before we could actually witness that supernova? If Betelgeuse went supernova today, would we see it on our sky? Yes or no? Arunsak says no. Why not?
Because it's so far, the light hasn't had enough time to travel to us.
And the fact
And
that I
how
just
long
saw
would it
him
take
being
before we saw
black
that
too.
supernova?
I don't know. Wouldn't I need to do some math to figure that out?
No.
You're asking for a guess?
Yo, I got a book you might like, Zeus.
Hold on, wait. You don't have to do any math because I told you it's 600 light years away. Arunsak, what's the speed of light in light years per year? What is the speed of light? All right, there's your test question. This is going to be your entire exam. Your exam is going to be one question. What is the speed of light in light years per year? You either get 100 or you get a 0. 180,000, Cameron, is miles per second or something. No, definitely not 186,000.
Isn't it 1?
Yes, Kate. All right, Caitlin just got a 100 on her final exam. Nicely done. Okay, everyone else gets a 0. Just Caitlin gets 100. The speed of light in light years per year is 1. So Arunsak, how long would it take us? How long in time would it take before we could witness Betelgeuse go supernova?
Did you say 600?
Yes.
Okay, 600 years.
That's my point. It would take 600 years. That means that if Betelgeuse goes supernova today, Betelgeuse going supernova today is technically in your elsewhere. You will never have access to this information. Eventually, of course, the light will reach you. It'll travel at the speed of light, and it'll bonk you off the head, and you'll see it go a brilliant flash in the sky. Sometimes people try to represent four-dimensional space-time when they do represent it as a grid. And now I'm going to talk to you about how gravity works and how it is influencing space-time around it. People refer to this as the so-called rubber sheet model. And let's take a look at this interesting picture here. This picture shows a tennis ball in orbit around a bowling ball, in sort of the same way that Earth orbits the sun. Let's imagine that this rubber sheet has a bunch of gridded lines plotted on it. And these gridded lines represent the coordinates of space and time, except we're kind of cheating and we're doing it in 2 dimensions because 4D kind of hurts the brain. In general relativity, Einstein discovered that what gravity was doing is gravity was warping the coordinates of space and time. Basically, it was curving the coordinates of space into time in such a way that when objects tried to travel past the bowling ball, they naturally followed a curved, and here's the fancy term, a geodesic. Particles traveling through space-time follow curved geodesics as they travel around a bowling ball. And Einstein predicted that not only will objects sort of orbit around a large mass because of the curvature of space-time, Einstein also predicted that the path of a photon would be similarly warped and curved by the coordinates of space and time. All right, now here's where the story gets really interesting and freaky. Obviously, if you're a professional scientist and you come up with this theory, you need to have to make some kind of prediction, some way that people could test it. And Einstein had one ready to go. Einstein realized that during a total solar eclipse, the disk of the moon would block the disk of the sun. And for a few short moments during the day, it would be dark enough for you to see background stars. He predicted that if you could have an eclipse, and that eclipse would take place very close to the positions of a well-known star, that we would actually see the star shift in its position. Remember that we plot the positions of stars through two coordinates, right ascension and declination. You can think of that as a position in space, x comma y. He predicted that the path of the star as it warped past the gravity of the sun would shift through space, and he predicted the exact amount of the shift as, I think it was 1.6 arc seconds. It was around 1 arc second of shift. And famously, the scientist Arthur Stanley Eddington went out to photograph such an eclipse. And I want to show you guys the picture of it. Hopefully it'll be high enough resolution here. Eddington eclipse, general relativity. Actually, first I'm going to show you guys. So let's get the image so that you can understand what's going on here. Hopefully it will be, no, that's too small. Tools, we're going to need a large image here. This, I think, is the photo negative. Let's type, I should have this picture in my slideshow. I don't know why I don't. What we need is the one where they mark the positions of the stars. Sorry, guys. Normally, this is the first thing that pops up, and it's not a hard photograph to find. I just, there we go. That's what I want. All right. Now that I've got the photograph, let's take a look at what's going on so that I can make some kind of sense out of this for you. Here's the cartoon depiction of what's happening. Function F5 58. Normally, the position of the star when it's not near the presence of a large mass is just a straight line. Earth is here, the star is there, and a straight line connects the two with the starlight. Einstein realizes, I'm sorry, let me try that again. I goofed that up. Normally, the Earth is here, and the position of the star is there, and the light travels on a straight line from the star to Earth. Einstein realized that if this took place during an eclipse where the sun was somewhat very close to the path of the position of the star, the curvature of the starlight through the warped space-time would actually make the star appear to shift by, I think, 1.4 arc seconds was the prediction. So no one had actually ever gone and looked for this. He said, I bet if you go out, look at an eclipse, look at the position of a star, you'll see its coordinates change by 1.4 arc seconds. People said, yeah, right, that sounds like bullshit. So Arthur Eddington went out and observed this eclipse, and here's his famous photograph. This is a photo negative in which he plotted the position of the star before and after on the photograph. Now, it just appears as a tiny little black dot because the star was quite dim. This shift, 1.4 arc seconds, was exactly what Albert Einstein had predicted with general relativity. And this was a holy shit moment, because anyone could have gone out and photographed an eclipse before this, and they could have made this observation and noticed it, and they could have said, WTF, what's going on here? Why is the position of this star shifting? What's so cool about what Einstein did is he imagined it, predicted it beforehand. People went out to look for it, and it was exactly there with the precise amount of shift that he predicted. Overnight, Albert Einstein became a legendary and famous physicist because he had proposed this insanely wacky thing. Gravity works by curving coordinates of space-time. And there enough was the proof in the pudding. And that is just one test of general relativity. We've had many since then. In a way, I want to show you guys a picture of a planetary orbit as seen through, as seen with the eyes of general relativity. And I'm going to end soon here, but just bear with me. There's this thing that you can see in science museums, like how many of you have been to the Boston Museum of Science? Is that something you guys have done before? All right, cool. I love the Boston Museum of Science, and I particularly enjoy the Mathematica section, where you can see so many of these concepts that we talk about in our class come to life. There's this thing called the gravity well. And it's basically just a very smooth gravity well. I think there's one in Hong Kong. Yeah. Where they roll some steel ball bearings. I don't know if I showed this to you guys or not, or if it was a different class, but they basically roll some very smooth steel ball bearings along a curved funnel. And this funnel has been curved with the same coordinates that the gravitational influence of a star would warp space-time into. And what you can see is when you roll these steel ball bearings along the curved surface, they go into a perfect Keplerian ellipse. The ellipse you see here is the same ellipse that Kepler discovered when he came up with his laws of planetary motion. It has an eccentricity. It has a semi-major axis. The only reason that stars or planets don't infall to the sun is because there's no friction in space. The friction, the very small amount of friction between the steel ball bearing and the plastic, eventually causes the orbit to lose energy, and very slowly it will spiral in towards the center of the hole. In other words, gravitational orbits are literally working by having objects roll along the curved coordinates of space-time. It's very cool. Once you adapt yourself to general relativity, once you have this view of gravity, a whole bunch of interesting consequences come out of GR, and we're going to need them to talk about black holes. So before I end my lecture, we're just going to list some of those consequences, one of which you've already experienced in your lecture, gravitational time dilation. Just as special relativity resulted in some kind of kooky effects, things like time dilation, length contraction, relativity of simultaneity, there are consequences of general relativity, effects that can only be understood by adapting Einstein's view of gravity. And you guys just saw one of them, the curvature of starlight. And this was the photograph that I just showed you, showing the positions of a star changing when it passes close to the sun. So the curvature of starlight in the presence of a mass. This not only happens when starlight passes close to the sun, it also happens when starlight passes close to galaxies. And I'm going to show you a dramatic example of that. In fact, somewhat of a better name for this, and these are kind of the same thing here, it's known as gravitational lensing. And I'm going to show you a picture of that before we sign off today. Another one that we learned about in our homework last week is gravitational time dilation. And that equation was familiar or simple enough that we could actually write down a formula for it. It's t equals the rest time over the square root of 1 minus, remember it was the escape velocity over the speed of light squared. The idea behind gravitational time dilation is time runs slow in the presence. Actually, I'm not feeling good about my spelling today. Time runs slow near a strong gravitational field. A few of you mentioned that movie Interstellar, where they had, you know, a dramatic example of this in that movie. There's also another concept called gravitational redshift. This became another confirming test of general relativity that was performed right up the street at Harvard University, where they actually fired a photon. They basically went into this tall building, I think it was at the physics department, and they fired a beam of light, let's call it a green laser, from the bottom of the building to the top of the building. General relativity predicted that the laser trying to travel upwards against the gravitational field would result in the laser beam being stretched out and undergoing a redshift, where the wavelength of light became slightly longer as it traveled through the gravitational field of Earth. The effect was really, really tiny because Earth is a weak gravitational field, but their instruments were so sophisticated that they measured this gravitational redshift. Gravitational redshifts can become very profound near the compact gravity of a neutron star. Light leaving the star actually loses energy and becomes redshifted as it leaves the surface. There are some others too, but these are some of the ones that I think are the most interesting. One thing that I would like to do to give you an example of gravitational lensing, and this will be my last moment with you here. Let's imagine, oh wow, I love that video. Let's imagine how this would work if light were to pass by a massive object like a galaxy. And here I just want to show you this cartoon picture. We see this all the time in our images of extragalactic physics, and I'll show you a dramatic one in just a moment. Here we are on Earth. There's the Chandra Space Telescope. And somewhere between us and a distant galaxy, it's called a quasar, but basically quasars are the bright nuclei of galaxies. And as you know, galaxies can have a tremendous amount of mass in them. Our own galaxy has close to 1 trillion stars. If an object is located directly behind your galaxy, beams of light that travel just astride the galaxy will undergo a warping and a curvature around the curved coordinates of space-time, and it actually can make it look like the galaxy appears twice, once here and once here. We know that they're the same galaxy because when we do spectroscopy, we see the exact same set of absorption lines. We can test and make sure that it's kind of like a fingerprint. And what this ends up looking like when you actually see a picture of galaxies, I want to show you this picture because it's very cool. Let's look up an image of gravitational lensing. Oftentimes when you see these, don't die on me now, internet. Hold on, let me try that again. Okay. Yeah. Take a look at this picture here. This picture is of something called a cluster of galaxies. Each one of those sort of yellowish, Control plus. Each one of these sort of yellowish fuzzy balls is an elliptical galaxy. So everything that you're seeing here is basically a galaxy. That's a galaxy, that's a galaxy, that's a galaxy. And you're seeing them clumped together in a structure called a galaxy cluster. Can you guys see these little arcs right here? These little blue streaks? That is gravitational lensing of more distant galaxies passing through the warped gravitational field and actually getting curved. One of the things that Einstein predicted is if two galaxies were exactly in line with each other, they would create something called an Einstein ring. And we have images of such a thing. Take a look at this legendary photo. Sorry, guys. Why? Why are you doing this to me? Here we go. When two galaxies are in perfect alignment, the yellow fuzzy ball is an elliptical galaxy, and this is a blue spiral galaxy in the background whose light has been smeared out into a perfect ring. You can actually compute the amount of curvature and the distance to the galaxies just based on the measuring the diameter of these rings. There's all kinds of clever math tricks. People use gravitational lensing all the time to measure the masses of galaxies. You can predict how much mass will be there based on the curvature of the ring. In fact, one of the most legendary Einstein rings, I think people call it the smiley face galaxy or something. Let's see if we can find, I just saw a picture of it. Well, bloody hell. This is the thing I want, but yeah. So people love this one. Here's an effective gravitational lensing, creating your little smiley emoji. So all of these, anyways, here's the point. None of this would be possible if general relativity didn't work the way Einstein says it does. Seeing images like this show us that photons are curved by the effect of a gravitational field, and they're sort of just supporting evidence that this theory of gravity is more powerful and more useful to us ultimately than Newton's theory of gravity. Today, general relativity, which started out being about motion, is our leading theory of how gravity works. And in one of the most dramatic examples, when a star, a massive star, finally dies, all of the gravity of the inner core of the star eventually inspirals into a singularity or a black hole. And black holes represent places where the curvature of space-time goes absolutely bonkers, so much so that even light itself cannot escape. And this is going to be the guidance we need to understand black holes in next week's lecture. Okay, that about does it for this class. I hope you enjoyed learning about general relativity. Today is a different kind of day. Normally we have a lot of work to do, but today was just about listening and having fun. Next week, we're going to have a lab. We'll have a lecture. I hope you guys have a great Thanksgiving. Try to stay safe and not catch the Rona while you're eating your turkey, okay? I think that's it. Do you guys need anything else from me?
There's no homework today? Why is that?
What's happening?
Oh, okay. So
I-
I tried to explain this at the beginning of class, but not everyone was here. When I thought about this week at the beginning of the semester, a couple of things crossed my mind. We would need like a little pressure release valve because each week we're kind of grinding away on labs and homeworks. We have no class on Thursday because of Thanksgiving. And I had a lab for us to do today, but I thought maybe you guys would like a little bit of extra time in your lives to go get your Thanksgiving ingredients, maybe just to chill and have like a little bit more of a relaxed day. We can get right back to the grind next week. Also, I know that you guys probably have projects. I have some intense stuff to do for my job, so I could use a little extra time myself. I don't know. I just felt like giving you the day off from lab. I hope you guys are okay with that. All right.
You're awesome.
Yeah, I know.
You have no idea. This is great.
I figured this is a time where people could use a little extra time in their lives, right?
Yes.
All right, cool.
Happy Thanksgiving.
So happy Thanksgiving, everyone, and I'll see you afterwards on next Tuesday. Okay.
Happy Thanksgiving. Bye.
Bye.